everyone, and welcome to Talk Nerdy. It is Monday, August 29th, and I'm your host, Cara Santamaria. This week, I want to give a big shout out to those of you who have made Talk Nerdy possible, especially by visiting the website, carasantamaria.com, where you'll find the Talk Nerdy stream, as well as places where you can support the show, like my Patreon page. You can also go to that directly by visiting patreon.com/talknerdy. This week's top supporters are Phil T. Bear, Pedro M. Rosario Barbosa, Stuart Ogg, Atomic Rod Adams, The Honorable Husband, Charles Payette, Jafe, Gabriel Felipe Jaramillo Gonzalez, Brian Holden, and Jeffrey Sewell. Now remember, Talk Nerdy will always be 100% free to download, so if you want to help support the show, you can do so by visiting patreon.com/talknerdy. You can also rate and review in iTunes and other platforms, and you can visit the Talk Nerdy store at carasantamaria.com, where I just got a new shipment in of beautiful hand-thrown mugs by Potter H.P. Bloomer IV. And I also have some wonderful leather goods like keychains and bookmarks that are all handmade, hand-stamped, and stained by Foster Leathercraft. All right, guys, without any further ado, I am really pleased to announce my guest this week. She's an astrophysicist at NASA's Goddard Space Flight Center over there in Maryland near DC, and she specifically focuses on galaxies. She studies how the stars and the black holes of distant galaxies form and how they change over time. But right now, a big part of her job is the James Webb Space Telescope. She's actually the deputy project scientist for the James Webb Space Telescope Science Communications. So that's a big part of what we are going to discuss today. So exciting. So without any further ado, here she is, Dr. Amber Straughn. Amber, thank you so much for joining me today.
Hi there.
Hi.
Thank you. It's good to be here.
I'm so excited when I meet a super interesting scientist on the internet and then I get to pick their brain and talk about all the cool work that they're doing. So this was, I don't know, just really serendipitous. I was talking about James Webb on the internet. Somebody recommended you to come on the show because you is one of your positions at NASA right now that you're kind of the outreach person, the communications person for the James Webb Space Telescope?
Yeah, so I am the official title is the Deputy Project Scientist for JWST Science Communications. So part of my official job on the project science team is to be sort of the scientist voice in all of our official communications that go out from NASA about the telescope. So it's a super fun job.
That's awesome. So from my experience with friends and colleagues that work mostly on my side at JPL, because I live here in Los Angeles, you're at Goddard, though, which is near DC, right?
Yes, in Greenbelt, Maryland, just outside of DC.
Cool. From my experience, I find that the culture at NASA, or at least at NASA JPL, is that there are scientists and there are engineers. There are generally significantly less scientists than engineers. The scientists oversee the science, the research questions, and then the engineers figure out how to make everything work so those research questions can get answered. Is that the case with James Webb as well?
Yeah, that's very much the case. They're the scientists, the astronomers, not only from in NASA, but really from the entire worldwide astronomical community that help to set the priorities for the science questions we want to answer. And then the engineers work alongside us to build these awesome telescopes that are designed to answer these big science questions. So it is a little bit of two different teams, scientists and engineers. But in the case of these big missions, the teams really work very closely together.
Yeah, really couldn't do it without one another.
Oh, absolutely. Yeah, the engineers build our awesome toys and and we tell them, what we need those toys to do.
That's so cool. So before we jump into James Webb and your background in astrophysics, I have to give a little bit of background for people who are listening that I had to push back our meeting here on Skype to have this conversation today by like half an hour because I was taking an aerial yoga class. You mentioned that you've been doing yoga for many, many years, haven't you?
Yeah, I have actually. I started practicing yoga consistently when I was in graduate school. So I was a huge stress ball, in grad school, working all the time, not sleeping enough, not taking care of myself. And then, and that was at Arizona State, where I did my PhD work. And then I discovered yoga while I was there, and it totally changed my life. I don't say that about many things, but yoga has been such an amazing grounding, balancing part of my life. It's fantastic.
Yeah, I have a long history doing yoga, but I've never been 100% serious about it. I've always been a little bit serious about fitness, and yoga is just kind of a part of that, but I've not been one of these people who's like really good about ensuring that I do it every day or every other day. But I've been having some lower back problems, and my trainer and I have been trying to work it out. And a friend of mine got a Groupon for this aerial yoga thing, this flying yoga. And so I went and tried it for the first time this morning, and it was so cool.
That's great. It's definitely on my list to try. I haven't tried it yet, but it looks like so much fun. So I'm glad you liked it.
It's like a lot of the positions that you do in yoga on the ground are limited because you're on the ground. But when you're in this big, weird fabric cocoon, basically, gravity works differently, and you get to do inversions, and it's really crazy. So anybody listening, I recommend it. It's super fun, but it also feels weird when all the blood is in your head.
Sounds fun. I'm definitely hoping to try it soon too.
Definitely. Okay, cool. So you mentioned graduate school. You mentioned the stress of graduate school. After graduate school is where you studied astrophysics, right? Is that was your focus?
Yeah. So I did my 4 years of undergraduate at University of Arkansas. Go Razorbacks!
Nice.
And I got my undergrad degree, my Bachelor of Science in Physics there. And then, I went on to Arizona State, where my PhD is actually in physics. But ASU was one of the places where I could get a PhD in physics and still focus on astrophysics.
Oh, nice.
So I sort of wanted that more broad PhD in case I did decide someday I wanted to go into industry or something like that. But I've stuck to astronomy, and I absolutely love it.
Yeah, and now you're at NASA. I have to ask, right? Because as a fellow Southern girl, I was born and raised in Texas, and I have family in Arkansas. I do detect your Arkansas accent, as I'm sure many people do. Is it, do you ever get grief for that as an astrophysicist, right? What some people would assume, or like quote unquote a rocket scientist, what some people would assume is kind of like the most heady, the most intellectual pursuit anybody could have. And you have this kind of quaint Southern accent. Do people ever call you out for that?
It's always in sort of in good fun. I never really get hassled for it. But it's funny when I go back home to visit family and stuff. Everyone there, all my friends think I've lost my accent.
Oh, how funny!
And I can tell myself a little bit too that it's not nearly as strong as it used to be, and that wasn't on purpose. I didn't try to lose my accent, but then when I'm around normal non-Southern people, everyone can hear it. So, but I don't mind it.
Oh, I love it. I think that Southern accents are so charming. They definitely remind me of home. I noticed, too, that a lot of my friends who grew up with me in Texas who left home, maybe went to New York or LA or other big cities and did lose their accents, it always comes out after a beer or two.
Absolutely. After a beer or two, or when I'm really tired, or when I've been back home around my friends and family, it definitely comes out just naturally. It just happens.
And so do you have a little bit of some hometown hero status? I mean, is everybody back home really kind of impressed that you are out there at NASA doing this amazing work?
Well, maybe a little bit, I guess. The town I grew up in Arkansas really is a tiny, tiny little town. It's called Bee Branch. That's the name of the town. 2 words, bee, like a bee on a branch. And I had 28 kids in my high school class, in my graduating class. So a tiny little rural farming town for sure. But a lot of my, a lot of the people I grew up with, teachers and stuff, are still there, and so I love to go back to my high school and go back and see friends and teachers from when I was growing up. It's a lot of fun. I love it. And, I really credit growing up in a small rural town to my love for astronomy, because the sky was absolutely beautiful and dark, and you can see so many stars. And so it really was, growing up under that beautiful rural sky that got me interested in astronomy to begin with. So I think it's, it's because I grew up where I did that I ended up in astronomy.
It's almost a little ironic, right, that you left this beautiful kind of idyllic town without a lot of light pollution. Now you are in a part of the country where you actually can't see as much in the sky except through the cool technology that you get to use.
Sure. Yeah, no, it's true. And the big Perseids meteor showers just a couple weeks ago, and I was sort of lamenting the fact that I wasn't back home in Bee Branch to watch that meteor shower because the sky is so light polluted here. But, I love working at NASA, and I like living in the DC metro area. So.
Oh, I love DC, and you have the Smithsonian institutions nearby. You have so many great things. Did you get to see any of the Perseids?
It was a little bit cloudy here that night, and it was really hot.
Yeah.
So I went outside for a little bit and didn't really see anything, and I
that's such a bummer. We were lucky enough to drive. We drove to a little spot that amateur astronomers like to visit called Fraser Park, which is about an hour outside of LA. Left around 11:30 at night, got there 12:30, just in time to set up the telescope and to set up all of our blankets before the moon set. And we got to observe until maybe 4 or 5 in the morning. I must have seen 50 meteor. It was insane. It was so great. Beautiful. Yeah, we really lucked out. It was, I forget sometimes living in LA where there is so much light pollution that it is not that hard to go out into nature, and that there are some really wonderful towns very close to LA where they, I think, respect the idea of reducing light pollution so that people can come and observe. It's very cool.
Yeah, for sure. The darkest sky I've ever seen, I think outside of the tiny town where I grew up, was up in Yosemite.
Oh, yeah.
My husband and I went camping there back when we lived in Arizona, and we spent about a week camped out in the park and went to Glacier Point, and it's just a stunning sky. It is really great.
It's like there's something about the elevation, you don't have a lot of atmospheric turbulence when you're observing, and it's a little bit cold, and you see the Milky Way, like it lights up the sky. It's insane.
Right. Yeah, it is so great. And now it's sort of ironic, as you mentioned, as a professional astronomer, I don't really get the chance to go out in the middle of nowhere and look up at the sky anymore. But when I'm home in Arkansas, I do try to do that. Take advantage of the fact that I'm under a dark sky and just really get back to that initial passion, that love, those questions that I had about what was up there and what made it all work and what's it like. I think that having those experiences really was formative to me as a kid, but I think on sort of a bigger scale, standing under a beautiful night sky like that is something that can be really impactful for anyone, whether you're interested in science or not. It's in some levels it sort of makes you ask existential questions.
For sure. Yeah, and it really can take your breath away, and sometimes we forget to just look up, and then when you do, you're like, oh yeah.
Right.
I can't believe that's all up there. And of course, there's only so much you can see with the naked eye. The darker the sky, the better. The more dark adapted your eyes are. If the moon has set early and you really get to enjoy that darkness. But there's so much beyond what we can see with the naked eye that you have the pleasure of exploring. So is your research focus, or has your research focus as it's evolved in your professional career, mostly been in these very deep sky objects?
Yeah. So even from the time I was a little kid, I knew I wanted to do astronomy, but I've always sort of been drawn to the sort of big questions of astronomy of, what is beyond what you can see with your eyes, and what is the universe like on big scales, with our eyes and under a dark sky, if we're really lucky, we can barely see the Andromeda galaxy. But other than that, every star you see in the night sky, of course, is a star in our own local Milky Way galaxy. And so just knowing that there are other galaxies that are out there that our eyes can't see, it's sort of tantalizing, It's like, what else is out there? What can't we see? And so that's what got me asking questions about what's beyond what we can see. How many galaxies are there? How do they all work together? How have they changed over, the course of cosmic history? Those are all questions that I'm really interested in very broadly.
Really cool. And so how does that sort of fold itself into this amazing position that you have now of doing the science communication, or kind of heading up the science communication on the science side of James Webb? Also, I'm getting ahead of myself. Maybe we should tell people what James Webb is.
Yeah, sure thing. So if people haven't heard of the James Webb Space Telescope, it's not a surprise because we haven't launched yet. But almost everyone has heard of the Hubble Space Telescope, which I think, as an aside, is just amazing that Hubble has become this cultural icon. Everybody in the world, pretty much knows what Hubble is. If you ask someone to name a telescope, they'll probably say Hubble. So in a lot of ways, Hubble really sets the stage for what we're doing in astronomy now at NASA. Just last year, we celebrated 25 years, a quarter century of Hubble being in space, which is absolutely incredible. And it's really not an overstatement to say that Hubble has fundamentally changed the way that we understand the universe. In really key areas, it has changed, lots about our understanding. And one of the coolest things I think about telescopes like this is that, every time we build them, we have this sort of defined set of questions that we want to answer with the telescopes. And that's great. That's how we design telescopes. That's how we learn how to build them. But every time we launch a telescope like Hubble, or in the future Webb, we learn things that we never expected. We'll end up answering questions that we haven't even thought to ask when we launch it. And that, for me, is one of the coolest parts about being a scientist, is just this idea that there are all those surprises out there in the universe waiting for us to figure them out. But yeah, Hubble has definitely, it's taught us so many things about the universe. One of the coolest things I think Hubble has taught us is that it's taught us about the size of the universe, that the universe is absolutely huge. So all these beautiful images that Hubble's given us, if I had to pick my favorite, it would probably be the Hubble Ultra Deep Field.
Oh, it's like my background on every laptop and every iPad ever.
It is such a beautiful picture, and it's I love that it's so beautiful, even to non-astronomers. You show that to a group in the public, and they love it. It's stunning. And the awesome thing about that image, the Hubble Ultra Deep Field, is that in this image, every little point of light you see in that image, almost, there are a few stars, but almost every single point of light is an individual galaxy. And all of those galaxies have, hundreds of billions of stars. And even so, that image with 10,000 galaxies is only a pinprick in the sky. It's this tiny little piece of sky. If you held out your pinky finger at arm's length, you could cover up this little piece of sky that the Hubble Ultra Deep Field covers.
That's crazy.
And so then, you easily do the math, expand that over the whole sky. And it tells us, Hubble has told us that the universe is filled with hundreds of billions of other galaxies. So Hubble, in a nutshell, has given us the size of the universe, and it's absolutely vast. And so I think that's one of the coolest things that Hubble has taught us. And of course, those beautiful images, like the Hubble Ultra Deep Field, in addition to being just beautiful, obviously, they tell us a lot about the physics of galaxies, about galaxy evolution, how galaxies are changing over time. So Hubble has sort of shifted our understanding of the universe, and we are poised to do that again, I think, with the James Webb Space Telescope.
And so Hubble has been around, as you mentioned, for quite a while. Obviously, it's very high-powered. It's incredibly technically, impressive, but it's old at this point. It's still working, and it's still working quite well, but it is old. What are the differences? What are some of the changes, the improvements that we will see in James Webb? Because is James Webb, in essence, sort of Hubble's replacement?
Well, we like to say, instead of being its replacement, it's the successor.
Okay.
So we certainly hope that Hubble will still be working when we launch the James Webb Space Telescope, because it will be amazing to have those two observatories working together. And so, like you said, Hubble's still working great right now. It's doing amazing science, and we expect it to keep working out, to the early 2020s, we hope.
Yeah, didn't it recently get a renewal? Like, it recently was announced that, like, Hubble, we're going to keep it out there even longer than we thought.
Right, right. So of course, the last time we serviced it was in 2009. And one of the
Mhm.
reasons that Hubble has lasted so long and been so incredible is because we've sent astronauts up to refurbish it 5 times. And
Wow.
so that last refurbishment happened in 2009. And
Mhm.
so at that time, it got new instruments, new batteries, new gyros. It was basically a new telescope after 2009. And so, of course, subsequently to that, we have retired the shuttle program. So we don't
Mhm.
currently have a way to get back to Hubble to repair it. However, it is still working great. So we have our fingers crossed that it's going to keep working well. But in the most fundamental sense, we're designing the James Webb Space Telescope to answer the biggest questions in astronomy that Hubble just can't quite answer. So yeah, Hubble has done amazing things for us, but there are a lot of ways that we've sort of pushed it to its limits. And so the Webb telescope is designed to go just beyond that, to see, in a literal sense, to see beyond what Hubble can see, and answer the next big questions in astronomy that we can't answer with any telescopes now in space or on the ground.
And what are some examples of those kinds of really big questions?
So there's sort of 4 broad themes that we have with Webb that we hope to learn more about the universe. The first one is we want to be able to see the very first epoch of galaxies that formed after the Big Bang. So one of the awesome things about telescopes is they are, in essence, time machines.
Mhm.
You look out into space, and the further away you look in distance, the further back in time you're looking. So when we look at objects that are in the very, very distant universe, we're seeing them as they were billions of years ago. And that sounds sort of trippy, but it's really just due to the fact that light has a finite travel time. The light bulb across your office took the light from that light bulb took a teeny tiny fraction of time to travel across the room to get to your eye.
Mhm.
The light from the sun, 90 something million miles away, takes 8 or 9 minutes to get from the sun to your eyes. So when you look at the sun, which you obviously shouldn't do directly, of course, but the light you're seeing from the sun is took 8 minutes to get here. And so you just sort of extend that out. So things that are more distant, the light takes more time to reach you. And so with Hubble, we've been able to push back and see very distant galaxies. We've been able to see back over 13 billion years into time to
Wow.
galaxies that were born 13 billion years ago.
So that's almost to the
It's
Big Bang.
almost, but not quite. When we see those most distant galaxies, and when I say see them, it's not in great detail. They're usually just a couple of pixels on our images, just a
Mhm.
couple of pixels of light, and they're tiny, and you can't see any detail. We just see the light. But what we can determine from those is that they are not the first galaxies. They're not pristine galaxies. And so what we hope to be able to do with Webb is to push back further, which we know we'll be able to do, and see the first epoch of galaxies that were formed after the Big Bang. So us astronomers talk in terms of redshift. The highest redshift we've been able to see with Hubble, we're pushing back to sort of redshift 10 or so. With Webb, we hope to push back even further, pushing towards redshift 20. And that is looking back to something like 500 million years after the Big Bang. So in cosmic times, really, really soon.
Mhm.
And so we can't see that epoch of galaxies at all right now. With Webb, we really hope to be able to see that first epoch of galaxy formation. So seeing the first galaxies is the first big goal.
Okay.
The second big goal is we want to learn more about how galaxies assemble and evolve over time. So when you think of a galaxy, what comes to mind? Well, like spiral
Ooh.
arms.
Yeah.
When you think of the Milky Way galaxy, or you've seen images of the Andromeda galaxy, it's this big bright blob at the center, and then spiral arms and stars, and they're big, and they have lots of very organized structure.
Yeah.
But the galaxies that we see in the distant universe, it's a completely different picture. They're oftentimes smaller, they're really clumpy, they don't have lots of organized structure. So this question of how we go from the sort of small, clumpy train wreck things in the early universe to the large, organized galaxies in the present day universe, That's still a big mystery in astronomy. We don't really know yet how all of that happens. So with Webb, we hope to be able to learn more about that whole process of galaxy evolution over the last 13.5 billion years.
Cool.
So lots of fun stuff there, and that's sort of my area of research. I'm really interested in how galaxies form their stars and their black holes and how those processes change over time. So I'm really interested in that particular part of what we hope to do with Webb. So that's number 2. Number 3 is we want to learn more about how stars are born. So that sounds really simple, right? Stars are sort of the building blocks of galaxies, but there's a lot that we don't know about how they're born. And the reason for that is that stars are shrouded inside dust when they're born. And so some of the most beautiful images that we have from the Hubble telescope are these sites of star formation, of newborn stars. So like the Pillars of Creation is a great example. That iconic Hubble image of those huge dust pillars where we know stars are forming inside.
And is that what we're talking about when we think of a nebula?
Yes, exactly.
And so it's nebulous. It's very dusty.
Exactly. And so stars are formed inside these nebulous cocoons of dust. And so we can't really, with Hubble, for example, Hubble is primarily an optical telescope. So optical light, you can't see through dust. I mentioned I lived in Arizona for 6 years, and we had these enormous dust storms. And if you're driving in and you happen to get stuck in one of those dust storms, you ain't going anywhere else. You stop. So we know from experience, our eyes, optical light, we can't see through dust. But the thing about the Webb telescope is it will be an infrared telescope. And so with infrared light, you can peer through dust to see these sites of star formation. So we'll have a new sort of way to look at the universe in infrared light to see these sites of star formation. So really cool stuff.
And will it also be within the visible spectrum, or is it only going to be an infrared telescope?
So it will have a little bit of capability in the red part of the visible spectrum. So it'll see a little bit of red light and then out into the infrared and out into the mid-infrared. So for people who speak wavelengths, it'll be 0.6 to 28.5 microns. That's its wavelength range.
And will the types of images, because, we think about Hubble as being this space telescope that has brought us, as you said, with the Hubble Deep Field image, just like these beautiful visual basically photos that we celebrate that help us to really understand our surroundings and as the general public to sort of get a sense of our place in the grand scheme of the universe. Will the infrared data that James Webb receives be able to be translated into those beautiful visual images as well? Do you think the public will get as profound an understanding from James Webb as they did from Hubble?
Absolutely. So the images from Webb will be spectacular. And so just to give you a sort of hint about what those images might look like, I've already mentioned the Pillars of Creation, the Eagle Nebula, one of Hubble's most iconic images. So that beautiful sort of greenish image in optical light and visible light that our eyes see, again, beautiful. But Hubble also has a little tiny bit of capability in the near infrared. So Hubble has an infrared camera also. So if you go and look up, so I'll challenge all your listeners to go and Google. And
I'm going to do it while you're telling me
to. To go and Google the Eagle Nebula or Pillars of Creation in infrared light. And because Hubble took an image of this iconic nebula in infrared light, and it is absolutely stunning. It is so beautiful. So that gives you just a tiny hint of the kind of images that Webb should give to us.
Oh, wow. Yeah, you can see it side by side in visible and infrared.
And those two images also, when you compare them side by side, optical and infrared, it gives you, it kind of helps to illustrate how you can see through the dust, right? In the infrared image, you really see all the stars shining through the dust. So A lot of fun.
Crazy how many stars you see. The other one really gives you a sense that kind of there just aren't that many. When you look at the visible image, it's like, oh, there's not that many stars in the sky, or they're really far apart, which they are, but like, wow, they're really far apart. And then you look at the infrared and you're like, yeah, no matter where you look, it's just billions.
Full of stars.
Yeah. Billions.
Exactly.
As Sagan would say.
Exactly.
That's so cool.
So those sites of star formation are another big thing we want to study with Webb. And then the fourth big science theme, and the one that I am probably secretly most excited about, even though it's not my own personal area of research, is, of course, exoplanets.
Ooh.
We want to learn more about planets orbiting other stars outside of our solar system. So when I was a kid, growing up in Arkansas, the only planets we knew of were the ones in our own solar system. And some of our most recent telescopes have completely changed that. So the Kepler telescope has shown us that planets are common. Planets are everywhere. Our Milky Way galaxy is literally teeming with planets. We now think there are more planets in our galaxy than there are stars. And that is an absolute paradigm shift in our understanding of the universe. And the really cool thing about Webb is Webb will be able to learn about details of these exoplanets. So the way that the Kepler telescope works is it stares at a piece of sky, it stares at stars, and it waits for the stars to dim in a periodic way. So it's watching a star, it gets a little bit fainter, and then it goes back to bright, and a little fainter again. And so that happens over and over, and that means that you have a planet transiting, crossing in front of it. So that's how Kepler and telescopes designed like it find these planets. But what we want to do with Webb is really an incredible thing. Is we want to watch those planets passing in front of their stars. And we want to zoom in and look at the atmospheres of these planets and watch the starlight filter through the atmospheres so that we can take spectra, take fingerprints of the atmospheres to see what is in them. So this is really hard to do because stars are really bright and planets are really tiny and their atmospheres are really small. And so it takes really, really cutting edge technology to be able to do this. But with Webb, we have it. We have some amazing instruments that we're going to be able to do unprecedented exoplanet science with this telescope. So really in really basic terms, the Webb is I think the next step on our search for life in the universe.
So cool. And will it work in some way similar to how Hubble has been? Because Hubble is a space telescope, meaning that it's literally like in orbit around Earth, pointed out into space, right? And is Webb going to also be in orbit around Earth?
So Webb won't be in orbit around Earth. It will be in space, but it's going to be in a different part of space. So yeah, like you said, Hubble orbits the Earth. Actually, it's fairly close. It's about 350 miles up. So it orbits the Earth once every 90 minutes. And of course, it's always staring out away from the Earth to look at things in the universe. Webb, as I mentioned, is an infrared telescope. So you can sort of think of infrared light as like heat radiation. So for the examples of the nebulae, the sites of stars and planet formation, they sort of glow at a temperature that falls within the infrared light range, if that makes sense. So
they're kind of like, it's like a flare camera, right? Like if you've ever seen one of these cameras that detects, like the FBI uses to see if somebody has a marijuana grow inside of their house or something.
Yeah, so exactly right. So if you've seen pictures on, National Geographic about how snakes see, right? Snakes see in infrared light. So yeah, there's different ways you can sort of, learn about how infrared light works. But the point is that if you think of infrared light like heat radiation, we want the telescope to be very, very cold, so it's not glowing itself. So its detectors aren't seeing its own glow.
Oh,
and
sure.
so for that
because then that'll be like a level of noise that it won't be able to read beyond.
Right.
Yeah,
that's exactly right. And so for that reason, we're putting Webb out into deep space. So we're launching it out. It'll be about 1,000,000 miles from the Earth. That's about 4 times further away than the moon is. And it will orbit the sun along with the Earth. So it's at this special point in space. It's called the second Lagrange point, L2, that we astronomers call it. And so that is basically a stable point in the Earth-Sun gravity system overall, where we can put spacecraft and they sort of hang out and they'll orbit the Earth at the same rate that the Earth orbits. They'll orbit the sun in the same rate that the Earth orbits the sun.
So it'll kind of be locked with Earth, but it won't physically be orbiting the Earth the way the moon does.
That's right. It orbits the sun along with the Earth.
Is it like tidally locked? Does it, stay facing the same direction as it moves around with Earth, or do you have to force it to do that somehow?
No. So the cool thing about the L2 point, the second Lagrange point, is it's of course a theoretical point in space, but it's a gravitationally stable point, or actually semi-stable technically, but if you put a spacecraft there, it'll stay there, and it sort of stays in the whole system of the Earth and the sun. Cool. So it will orbit at the same in the same spot roughly when it orbits around the sun. So but it's not locked in the sense that and in fact we want to be able to, and we will be able to point it.
Oh, cool.
So we'll have propulsion, and we'll have reaction wheels on the telescope so that we can point it in different ways, different places in the sky to observe whatever astronomers want to observe.
And so you'll be able to communicate with this thing from the ground, but you're probably never going to be able to visit it per se, to service it. That's right.
So it was not designed to be serviced. Of course, being so far away, it's 4 times further away approximately than humans have ever been. So it is certainly not designed to be serviced by humans. So it's different from Hubble in that sense. When people think of Hubble, they think of Hubble with the astronauts, which is awesome, right? That's so cool.
Yeah.
It's one of the coolest things about Hubble, I think, is that, and that's one of the reasons I think that the public feels affection for the telescope, which is so funny. But we think of people going there, actually physically going there, and that's such a cool part of Hubble's legacy. But we have to remember also that Hubble is an exception to the rule. All the satellites that we depend on for our daily life, GPS and our telecommunications, all of those are designed to work when they get into space, and they're not serviceable. And all the other space telescopes we've ever built, like the Spitzer telescope and Chandra and all the other space telescopes, same thing. They weren't designed to be serviced. And so Webb is in that category. It wasn't designed to be serviced. So it has to work when we launch it. And that's one of the reasons that it's taken a long time to build, very difficult engineering, and a really, really extensive, comprehensive test program. Because it does. It's a one-shot thing. It's got to work when we launch it. And so we're spending really the majority of the next couple of years with really extensive tests to make sure it works when we launch it.
It's also like crazy big, isn't it? I feel like I've seen images of these mirrors laid out almost in a hexagonal, like a beehive sort of pattern.
Yeah, it sort of looks like a beehive or a honeycomb. Yeah. So the mirrors themselves are hexagonal shaped. The primary mirror of Hubble, to give you an example, is about 2.4 meters. And the primary mirror for Webb is 6.5 meters. That's about 22 feet across. So in terms of, it's huge. In terms of area, it's about 7 times bigger than Hubble in terms of area. And then overall, the whole observatory is, it's absolutely huge. It's by far the biggest telescope that we've ever launched into space. Hubble is about the size of a school bus, roughly, if you think of it. Webb is it's about the size of a tennis court, and it's almost 4 stories tall. So
what? I'm trying to compare it to my 8-inch telescope. I have
Yeah.
a really nice 8-inch Schmidt-Cassegrain telescope, and honestly, when I take it out under deep in or dark enough skies, I can see Messier objects that are really far away. I can
Yeah.
see galaxies, I can see some nebula, I can see globular clusters, and
Hmm.
that's with an 8-inch telescope.
Right.
Like, this is crazy, like a tennis court size
Right.
telescope.
Yeah, the engineering behind this telescope absolutely blows my mind. I mean, I'm a scientist, so I'm really excited about getting that data back after launch. But just just watching, being here at Goddard and watching this thing being built, watching the pieces come in and being integrated together, it is really incredible. And it's given me really a new appreciation for cutting edge engineering, because that's exactly what this telescope is. We had to, at NASA, invent something like 10 brand new technologies just to build this telescope. It
Wow.
really is cutting edge stuff, and it's awesome. So yeah, just the size of it is being so big presents all sorts of engineering challenges.
Oh, for sure. The bigger it is, the harder it is to get up there, right?
Right. Well, and also, of course, we don't have a rocket that's big enough to launch the thing fully deployed. So it has to fold up, and then it deploys once it's in space like a giant space transformer.
That's so
um,
cool.
so yeah,
Maybe
it's
a whole
just
new children's cartoon.
exactly the deployments on this thing are it's absolutely incredible. And if you go to our website is JWST, James Webb Space Telescope, jwst.nasa.gov. We have all kinds of fun stuff on there, images of these stunning mirrors being built and integrated, and then also we have a deployment animation video that
Nice.
shows in detail how these animations happen. And so yeah, the engineering, talk about extreme engineering. That's what we're doing with JWST.
So if you had to compare what you think is more crazy, is it the transformer kind of component, the unfolding, the origami of James Webb, or the sky crane of Mars Science Laboratory?
Yeah, so they're both really good examples of extreme engineering. And the thing that we joke about with our Mars friends is that they had 7 minutes of terror, and we have 2 weeks of terror while
Oh,
all these
wow.
deployments happen. So it's going to be a tense 2 weeks, which is about how long all those deployments take, waiting for all those things to happen, so that we have a telescope that will work.
So cool. Do you ever, just to kind of be zen when you're at work, I would assume, maybe I'm wrong, at JPL, for example, in the big giant clean room, they have the big observation deck, so you don't have to be scrubbed in. You can just sit above and sort of watch down in the clean room. Do they have one of those at Goddard?
Yes, they do, and it's awesome. The clean room that we have here at Goddard, where we're building Webb, is it's the largest clean room in the world of its type, and so it's
Wow.
massive. I mean, it has to be to accommodate this this huge telescope. But yeah, I go over there usually once a week or so, and just sort of hang out at the window and watch the techs, the engineers working on it, and it's surreal, to be able to see this machine that we human beings have made, and to think that it's going to go to space and it's going to sort of unlock these mysteries of the universe. It really is. I mean, I have to pinch myself sometimes. We live in such an amazing world where we're able to do these things.
I love that. James Webb is a long project. It takes, it's been from conception to now the engineering and the actual fabrication to the launch and then to the maintenance and all of the data collection while it's up there.
Mm-hmm.
It's like some real job security for you, isn't it?
Yeah, actually, it really is. We started thinking about what the next big telescope after Hubble would be, shortly after we launched Hubble. So in the mid-90s, we started thinking, all right, what's next? And so people spend their entire careers working on one mission. There are people at NASA that this has basically been all they've ever worked on.
Isn't it fun when you get to meet somebody who's elderly, who was like involved in the earliest conceptions of a project, and it's kind of their baby that they finally get to see go to space?
Yeah, exactly. It's a lot of fun. And everybody at NASA seems to have that. It is. It feels like it's like a kid.
Mm-hmm.
You just spend so many years pouring your heart, your life into these projects. And so, yeah, people are really really connected to the projects that they work on. It's I think one of the most awesome things about working at NASA.
Yeah, I love that. And you're obviously quite young. You finished your PhD in what? I was looking at your background, like 2008. Am I
Yep,
wrong?
2008. So
Yeah,
yeah,
so that was not long ago that you have been basically working beyond graduate school as a professional astrophysicist. And you pretty much started at NASA as a fellowship or a postdoc, right?
yeah, that's right. I when I was working on my PhD, I had a graduate fellowship through NASA it was called the Jenkins Fellowship, which is an amazing program. It was for women and underrepresented groups in STEM, in the STEM fields.
Very cool.
And so then after that, yeah, I got a postdoctoral position here at Goddard, and then got hired on as a civil servant astrophysicist. So it's been a fun ride, and I've sort of been involved in the Webb project since I was a grad student. My thesis advisor at ASU is one of the interdisciplinary scientists, one of the university scientists on the Webb team.
Very cool.
So I've been involved in it, a little bit since grad school.
Yeah, so you've already dedicated so much of your professional career to working, on answering the research questions about galaxy formation that you're interested in, but also on this one specific mission. And obviously there are many more years to go, but this may not even be the defining mission of your career because your career is still so fresh.
Right, that's true. And the fun thing about being an astronomer is we can always think of bigger telescopes. So we're definitely already thinking, and not only thinking, we're already building the next big telescope that will come after Webb. And so that's the WFIRST telescope is the acronym, the Wide Field Infrared Survey Telescope. And we're already building that now here at NASA. And so the hope is to launch that in the mid-2020s. So it's different from Webb, but it's complementary.
Very cool.
Webb is designed to sort of do what we call like pencil beam views of the universe. So you can think of both Hubble and Webb sort of take little tiny pictures of the sky. It's almost like if you look through a straw, right? It's this teeny tiny piece of sky that Webb sees. The Wide Field Telescope, WFIRST, it sees a field of view that's 100 times bigger than Hubble. So
which is still probably very small. But.
Still very small, but it's a different design.
Yeah.
It's a different design of telescope that's designed to do whole sky surveys that you really can't do with telescopes like Webb and Hubble. So it'll be complementary. That particular telescope is keyed in on two big science questions. One is a new way of looking for exoplanets, so exoplanet science, and then also to discover more about dark energy.
Oh, nice.
This mysterious thing that exists in the universe that actually makes up most of the universe. That we have no real idea what it is. So that's another really cool mission that is coming down the pike at NASA. It's always something new to do, which is a lot of fun.
I'm just trying to envision the vast quantities of data that a wide field telescope would gather. I would not want to be in charge of cataloging all that data.
Yeah, and we have some work to do to figure that out.
Yeah, how do you store it? How do you, what are the algorithms to dig through it and find what's interesting? Isn't it funny sometimes how when there's new technology that comes out that can basically fire hose so much data, just being able to sort that there are people whose dissertations now, they're still just digging through probably early observations from Hubble.
Absolutely, yeah.
It's so cool.
Yeah, it is. It's a lot of fun. Lots of data, for sure.
For sure. Yeah. A lot to work with. So if you are a brand new student of physics, you ultimately want to study astrophysics, and these research questions are interesting to you, don't worry. There's still plenty of data to sort through.
Absolutely.
You're not too late to the party.
And, it really is cool how all the data from these NASA telescopes are public. Anyone in the world can go download Hubble data, not just the images, but the actual data, the raw data, and do research on it. So it's sort of, open source in that sense.
I love that. And you know what? I'll tell you as a journalist, the fact that basically all of what NASA produces and provides as public domain is incredible, because one of my day jobs is that I work for a public television station here in Los Angeles, KCET, on a TV show that's beautiful and well produced, but we have no budget. We're public TV. And so I recently did a story on the Europa mission, the upcoming mission that is being planned right now at JPL, and the animations and the images and all of the beautiful assets that we get to basically just use from NASA because they're available to the public. You never get that with other institutions, and that's because our tax money is what goes towards funding NASA. And it's like you said, you're a civil servant astrophysicist.
Right. It's a public resource. It's publicly funded by the taxpayers, and so therefore it's all publicly available, which is a great thing. And I really think NASA is one of the, of course I'm biased because I work here, but it's one of the coolest things that the government does. A lot of government programs, very good, needed, necessary programs, are about sort of helping, right? They're about making things less bad, about helping people in need and those sorts of things, and absolutely critical. We need those programs. But NASA is different in that it's more about making the world better in a different way. It's about stretching our boundaries and sort of going beyond what we're capable of. And in the end of the day, I think it's really about hope. It's about hoping for a better future and for realizing our dreams as human beings of exploring our place in the universe.
I love it. And, as an American citizen, as an individual who is a part of the public who does pay my taxes, it also gives you a really, I think, strong sense of almost ownership, even more than just inclusion. There is a little bit of a sense of ownership over all of the amazing things that are happening at NASA. Like, that's for us. That's ours. We're a part of that. And I think that just makes it that much more profound. And it reminds us, when we remember our link to NASA, as just regular citizens and voters, that we're all in this together, which is just so cool.
Absolutely. And also, being having this pride in NASA as a U.S. citizen is awesome, and I'm really grateful that I think the public, our U.S. public, seems to think NASA's worth it. That NASA's worth the investment. So that's really good, I think. Of course, NASA, the current budget is a tiny fraction of what it was in the Apollo days.
Yeah.
So sometimes people seem to look at NASA, well, why aren't we going back to the moon, or why aren't we doing awesome things? But oh my gosh, NASA is doing really awesome things. We're planning to go to Mars, not just planning, but we're working on the technology to send humans to Mars. That's incredible. In addition to astronomy, we're working on satellites that are studying our Earth, our climate, our Earth home system, to try to figure out how the Earth is changing and how the climate is changing. And that's obviously such a huge issue that we have to deal with today. So NASA does a lot with
very little. I mean, when you think about, right, if you think of our entire budget for the entire, country as $1, NASA, I think right now is operating on half of 1 cent.
Half a penny. Yep. That's right.
And if we were to just move that to 1 penny, you think about it, it's like, oh, it's a penny. It's 1% of the overall budget. That's doubling NASA's budget.
Exactly.
That's 200%. I mean, that's amazing. So that's definitely something that is, I think attainable. And this is where I always encourage my listeners, of course, especially those of you, or pretty much only those of you, but maybe especially those of you who live here in the States, to put pressure on your representatives and to reach out and to write letters and to make the phone calls, because that they have to listen to their constituency. Otherwise, they won't get elected. You have to tell them what you want. And ultimately, if there's enough political will, they'll do it. They will. That's how democracy works. And the great thing is that NASA is a truly democratic system. So yeah, I can say that, you can't, but I'm allowed to.
That's right.
But before we go, Amber, because I know that you have so much work to do, it's so nice of you to take the time out of your day to chat with me. Before we go, I have to ask you, because I ask everyone who's on the show the same closing 2 questions, and I'm always fascinated by the differences in their answers. And so sorry to throw this on you because they're kind of big picture. They're sort of epic. It's a lot to take in, but here they are. And usually I like to go in this order just so we can end on a positive note. Mm-hmm. The first one is, when you think about the future, in whatever context is important to you right now as you're thinking, whether it's personal, familial, or really big picture, like global, what is the thing first that you're most concerned about? What keeps you up the most at night and kind of worries you the most? But then on the flip side of that, the second question is, what are you really optimistic and hopeful for when you look to the future?
Yeah, those are great questions and really important questions.
But they're kind of evil, right? It's like, oh gosh.
Well, I think for the first one, for me as a scientist, it definitely is climate change, mm-hmm. and more than I shouldn't have even said as me as a scientist, as me as a human being, with people in the world that I love and care about. Climate change is a big problem, and I think the data that we're getting, even just in the last week, we just heard that July was the hottest month ever recorded in recorded history. Mm-hmm. It seems like since we started talking about climate change, we've always talked about it in terms of future, but it is happening now, and it is severe now. The floodings in Louisiana, the things that are happening in our world today due directly to climate change it's happening now. And so that really scares me. Yeah. I want to hope that we can pressure our elected officials to take some big change, take some actions to make mm-hmm. change. But at the same time, I think it's also on us. It's on us as citizens of the planet to do what we can to try to to make the world a better place, to mitigate our own carbon footprints, to, just do what we can to help it, because it is happening now. So that really worries me.
I'm with you on that one for sure. And I think the vast majority of the listeners are as mm-hmm. well. But there's obviously got to be some things out there that you're excited about, that you're optimistic about. Absolutely. And even just my day job, like I said, pinch myself. I work at NASA. It's awesome. And being able to work on these projects like the Webb Telescope and the WFIRST telescope coming up soon, it's encouraging to me, because I think it's all built on this very fundamental sort of visceral idea that we as human beings are meant to explore. We have it encoded in our DNA to go out and study our surroundings and push our boundaries and learn more about this world that we live in. And that exploration happens in an astronomer sense, in terms of learning more about the universe, but it also happens in the real sense of exploration of sending humans to Mars and further out into our solar system. So that idea that we have this sort of drive instilled in us to learn about the universe and to explore, I think it does give me hope. And it gives me hope to know that we as humans can build these amazing things. We build these awesome machines to learn about the universe and to explore. So I do have hope in the future. Yeah, really, how could you not when you think about it? I mean, the feats of engineering, the science, it's literally awesome in the true sense of that term.
Totally agreed.
Well, Amber, thank you so much for joining me today. This was so much fun.
Sure. Thank you so much for having me. It's been a lot of fun.
I learned a lot. And everybody listening, thank you for joining me week after week. I'm really looking forward to the next time we all get together to talk nerdy.